Hi, today we'll be going through differentiation. What is differentiation? Differentiation is a technique we use to find the gradient at any point on a line. And it can also be used for other things as well. But for today's case, we'll be using it to find a point on the line. So how does it work? So we're going to cover what's known as differentiation from first principles. So what is this? Essentially, what we are doing is do you know the formula that we use um for finding a gradient, right? If you don't remember, it's y minus y1 over x minus x1, or any sort of variant of this, right? So this is the gradient. So what we are actually going to do is a variation of this. Let me just move this over. So we're going to do a variation of this. So what we're going to do is we're going to have f x plus h minus f of x over h. And we're going to have that as the limit tends to infinity. Sorry, h tends to, the limit of h as h goes towards 0. Now, why h goes towards 0? Now, h is the distance between here. We got x naught for point A and x naught plus h for point B. So the difference between the two is h. And that's where we get the h from, because we've already done, just to show you, this is like saying f of x plus h minus f x fx minus x naught plus h minus x naught, right? The x naughts just cancel out, and obviously limit as h tends to 0. Okay, so that's essentially the same thing. Now, what is h? H is very small. It's a very small number. And why do we want a very small number? Well, if h is very small, that means the difference between the gradients at point A, difference between gradients at point A and point B are going to be very minimal. That means when we do our differentiation, essentially the number we will get for the gradient will be accurate, because the difference between them is so small that the gradient's essentially the same. So that's why we have h as the small number. So let's say we have a line here representing the gradient at point A, right? And let's see, I have another line representing the gradient at point B. Now here they look very different, right? However, if you were to make this, shrink it down infinitely smaller, this would be not noticeable, right? So that's essentially the idea behind it. The difference between these two gradients of the pink and the lighter pink line is so minimal that, although if you were to go close up, they would be different. But looking back, it would be so, if you were to zoom out way back, there wouldn't be that much different. Of course, here you can notice the difference, but if it was, microscopic, you wouldn't notice. So how would this run through an example? So let's say we have an equation. Let me just copy this so we don't forget. So let's say we have this equation and we have y is equal to, we have this function y is equal to 2x, right? Just for the first example. Now, obviously the gradient would be 2. If anyone remembers the formula, how to find the gradient would be 2. But we're just going to use this as an example, just for illustrations purposes. So, so let's say we put this into the differentiation expression, right? So the function is y is 2x. So you got 2 x plus h minus 2x over h. And the next step, that would be 2x plus 2 minus 2x over h, 2h, sorry. 2x plus 2h minus 2x and over h. Now, the 2x's cancel out. So now, and the h's cancel out. So then the limit of h as h tends to 0, limit as h tends to 0 is just 2. And that would be the gradient, right? And obviously anyone remembers how to find a gradient that is the number in front of the x, it would be correct. It's the same thing. So now let's do a slightly more complicated example. Let's say we have y is equal to 2x squared plus 3. So let's see what it looks like now. So the limit, let me just make this clearer. Okay, so that's the formula there. So limit as h tends to 0 so sub it in the x plus h where x is. So we get 2 x plus h squared plus 3 minus all of x, 2x squared plus 3 over h. So doing the calculations, say we expand the bracket, so we got x squared plus 2xh, because we'd have xh times x times h and x times h, so we add them together, get 2xh plus h squared plus 3 minus 2x squared minus 3. So we put in this in, we remove the brackets and put this in h. Now the limit, so h tends to 0. Let's say we can cancel out the 3 because positive 3 minus 3 is 0. So let me expand the brackets now, 2x squared plus 4xh plus 2h squared. This is squared. Minus 2x squared over h. So now we're going to cancel out 2x squared, and we can cancel out the h. the limit as h tends to 0, you have 4x plus 2h. Now, if the limit tends to 0, that means h becomes 0, and then we're just left with 4x. So the gradient is 4x, and let's say x, we had a point, right, where x is, let's say x is equal to 2, right? So first of all, let's see what point that would be using this example, 2x cubed, 2x squared plus 3. So let's copy this here. So say x equals 2, substitute that into the equation. So that means y is equal to 2 squared plus 3. That would be 8 plus 6, 11. So at point 2, 11, we're trying to find the gradient. So what would be the gradient? Well, we can use the form what we found, right? So we said that the differentiation is, so the symbol for differentiation, I didn't actually introduce this earlier. It's this, dy dx. So this essentially is the difference between the y's and the difference between the x points and y, difference between the points in x. So so we said earlier that's 4x, right? So then we're going to substitute that in. So if x is equal to 2, that means dy dx is equal to 4 times 2, which is 8. So the gradient at point 211 is 8. So thank you for watching. Go through the questions yourself, read through everything. Yeah, so let me just make this clear. That's use the symbol dy dx. Fix that. So yeah, so dy dx, let's zoom in a bit. So dy dx is a limit as h tends to 0 of x for function x plus h minus fx over h. So that's the formula to remember for first principles. Thank you for listening, and hope to see you again next time.